Hi, everyone. Someone asked a question on whether we have a quiz on Friday, and the answer is yes. You'll have a first quiz on Friday, and it shouldn't take more than 15 minutes. Yes, it is in class, so and it includes today's material, but would be mostly based on the previous lecture. But yes, everything that was covered up until Friday can be part of it. And yes, it will be in class, so we're probably going to wait the usual 10 minutes so everyone is in, and then we will start the quiz. And the quiz will be on Quarkus. So we're testing the platform for the first time right now with our TAs. And I think everything should be fine, and we will confirm that it will be on Quarkus. Yes, it will be mostly multiple choice questions, so we want it to be auto-graded. Yes. Again, remember, this is not in order to grill you. It's more like an enforcement thing to make sure you read through the material as we go, not towards the end of the semester. So that would make sure you read through the lectures, you paid attention, and usually if you just do that, you should be able to handle all these questions easily. So while we're waiting a few more minutes, there is a little bit of, we're all learning from the first week of this unusual semester. And we're trying to adapt and make changes to make your experience better with my TAs. One thing I noticed myself that from my perspective that I would like to improve, and I hope you guys will be willing to help. So obviously, if it would be a normal lecture, I would see you guys in front of me, I see your faces, and it's very helpful because it helps me to see your reaction to the speed of how fast I talk or how puzzling certain topics are. And right now, when all of you disable your cameras, I don't see anything. So what I suggest, if you are comfortable, at least sometimes turn on your camera, at least some of you will do it. I would at least get a feeling that you had a presence in the room, and I would look at you and can see how you react to certain topics I cover, how you react to jokes and things like that. So essentially my ask to you, if some of you at least can turn on your videos, not the the sound, but just the videos, that would help me to understand how you react to things. So I would really appreciate that. You don't have if you don't feel comfortable or the environment doesn't allow you to do so. Well, just make it pleasant to everyone. So just wear the comfortable clothing, but make sure you wear something. Yeah. And thanks a lot. So again, as I said, you can turn it for some time and then switch turns and whatever you like. But if at least some of you will do it, that's helpful. I hope it's not only helping me, but also you would at least recognize some faces of the people that I knew in class. Right now, it's all really not, visible, right? You just see some names. So this is from my end. From the lab side, so there are a couple of updates we're gonna happen. First of all, I guess from TAs, the ask to you is making sure that you all guys, when you log into Zoom, right, you log in with your first and last name. It helps you to know whom they're talking to, right? And they let you into different rooms, breakout rooms, or the green rooms for the labs. So that's important. Another thing that we will change for the labs is to make sure there is less confusion in who goes when. We will post, some of you probably have seen the Piazza post. That's what we suggest to change for the lab, so you guys don't waste your time. So we're gonna, like 1 hour before the lab, we're gonna post the list where you can get a slot on when you will be talking to your TA and will be graded. So you can pick the time that's the best for you on the first come, first served basis. And then essentially the TA will start the tutorial by covering some basics there, maybe some, some hints. And if you're ready with your lab, which is ideal, then you come when you're ready, right? Ideally, you should finish most of the lab before the lab, but if something that you didn't have enough time to fix it, you can still finish everything during the lab and then just put yourself towards the end of that lab. Okay, does it make sense? And thanks a lot for everyone who turned on, your videos. That's really helpful. Thanks a lot. Okay, so we will keep you posted about other changes related to labs. And if something is unclear, please put your responses on Piazza. So things will be settled up in a few weeks. We're just trying to make sure it's more comfortable because on Monday, it happens that some people were waiting very long and they were not sure when they're going to be called out. So we want to minimize that in the future so you don't waste your time. So when, if you're ready with your lab, you don't need to wait for 3 hours until you're going to be called. You know when exactly you're going to be called for grading. Sounds good? Okay, so let's see whether I had any questions here. Yeah, you can use whatever thing you like for your virtual appearance. Can we get the lecture slide posted before the lecture? I got these questions before, I answer it again. The short answer is no, mostly because I have some questions in the lectures that you want to answer live, right? So I'm gonna, stop my animation and say, please answer this question. If I'm gonna post all the slides before the lecture, the whole novelty of these questions are gonna be completely gone. So the slides will be posted and videos right after the lecture, but not before it. Okay, hope it makes sense to everyone. Okay, if you really want to know roughly how the lecture is going to look like, you can look at the previous instances of this class from downtown or Mississauga. They are roughly the same. So if the content-wise, you can find that easily. Yeah. Okay, so let's start. So we're back to the week 2 of computer organization class. Hopefully you still remember who I am. So some lab tips. Log into Zoom for the time slot instructed. Make sure your name matches your Quercus registrations. Make sure to finish the work that needs to be done before the lab. So ideally you finish most of the lab before that. So maybe some minor things still don't work. Then what happened in the lab? Usually back when we can meet in person, there was also a very log part of the assignments and you need to work on the real boards. And that was sometimes difficult and you need help of the TA. Right now you do everything in Logisim. So everything can be done beforehand, right? And if you had any challenges, obviously post questions on Piazza, as some of you already did. So the main thing for you to show, what really when you show your work to TA, you already know whether it works or not. So the TA, most of the time, TAs are spent for you to explain that how you did your work. So how you come up with this design or that design. So most of their questions, they quickly test that your stuff works, but then they ask you a lot of questions about how things work. So be ready for these questions, right? This is the only way to them to understand that you did the work yourself. Remember, you're supposed to do all this work yourself. Okay, so don't store your files in any shared folders on the lab machine. So there's no academic offense because we have no way to figure out who's, took the files from whom. Back up your work, make sure you don't lose anything. Use, USBs, Dropbox, OneDrive, anything that works for you. And keep an eye on your quota if you use something big. Okay, so we'll start as usual with a quick recap on everything we covered in the last week. So a little bit of repetition here. So let me handle a question here. The lecture slides today will be posted as usual on the course website, similar to the last week. So everything will be posted there. Videos, slides, everything, reading materials, everything you need to do. It's not up now, as I said, and I think I explained why I'm not posting it ahead of time. Okay, let's move on. Okay, so we learned about their different gates before, right? And we're going to use them a lot in this lecture. So AND gates, this is how it looks. And this is its truth table. AND gates is very easy, right? If you get at least 1 zeros, either A and B, then the output is 0. Otherwise, when it's 2 1s, then the output is 1. There is obviously another popular gate, OR gate, and that's its truth table. This is NOT gate. This is XOR gate, and its truth table. We're going to use them as well. And, the joke happened before. So in other lessons, you can repeat the material, but never repeat your jokes, right? So no Bill Gates today, but I still owe you another joke about the gates. So here it is. It's called a marriage logic gate. I don't know how many you've seen this before, but essentially, you had 2 inputs. You had a man and a woman in the input, and that's a good advice from someone who is married like I am, something to, to keep your marriage alive. So follow this marriage logic gate. So first of all, if the man is wrong and the woman is right, already the result that the woman is right, right? If man is right and the woman is right, then woman is still right, right? If the man is right, but the woman is wrong, then the woman is still right. And if both are wrong, then the man is wrong. So it's very helpful logic for the future. Okay, so jokes aside, let's see whether we had any questions or just smiles. Okay, so yeah, more or less 90 gate. Yep. Okay, so that's the logic gates. A second important things we cover is the transistors. Transistors, remember, are made out of doped semiconductors put together, p-n junctions, right? Everything you learn in the first lecture is like a resistor, but can change its resistance. That's the key thing you really need to remember for that at the end of the day. We had materials that can be manipulated such that they either we can manipulate the resistance, so the charge sometimes goes in and sometimes it doesn't. So it really have two states, switch on or off, right? As how you switch on your lights at home. So this allows us to build in transistors, and they're controlled by electrical signals, and we use a certain type of them. We go into details of that, called MOSFETs. That most transistors you use in all the devices, your cell phones, your laptops, everything is built out of those transistors. And you know, now you should understand the physics underneath of it. So really, from your standpoint, the MOSFET looks like this. There is a source, there is a drain, and there is a gate. And gate, you can apply charge to make it on or off. That's the simplest possible symbol for MOSFET transistors. Remember, we showed how we can take those basic transistors and build all these logical gates out of it, right? So there are those transistors, like for example, here, this is an AND gate built from 4 transistors. This is an OR gate, also built from 4 transistors. And this is a XOR gate, as you can see, built from 8 transistors. So now you can feel like they're not equal anymore. Even from your math course, AND, OR, XOR are all just symbols, right? They're all equal. When you start to physically build them out of real transistors, they can have different values. And as you learn later in this class, the most efficient one so far in the current manufacturing process is NAND transistor, NAND. So that's the most efficient. So you usually try, and if you try to physically build it, that's what you're trying to use most. Okay, so so now we're going from gates to circuits. And in this lecture, the goal is how we can use these gates as the building blocks to build larger circuits to represent complex logic. So we're going from the very bottom, from electrons, junctions, keep going up and up. Eventually, you can see how the processor, the whole computer can be built. But right now, we're mostly focusing on the basic functions. So the beauty of abstraction in the system design, remember I told you about that, but I repeat it once again, is that from this point on, you can just use symbols AND or XOR. You don't need to think about MOSFET p-n junctions anymore, right? You can just write AND, you know how to build it. You don't need to worry how you're going to build it every single time. So right now on this lecture and moving on, we're going to just use the symbol for AND or NOT gate. And these logic gates allows us to create output values based on one of the more input values. So they all correspond to some Boolean logic that you learn in one of your math classes before. Again, you can see here there are 2 truth tables, 3 truth tables for AND, for OR, and for NOT. Okay, so how we can build Boolean expressions. So we would like to represent Boolean expression using logic gates. So let's say someone gives us these complicated equations here, right? Y equals A or B and not A or not B or C, something like that. So how are we going to build it? Well, we're going to build it again, bottom to top, right? I'm going to take the first, part of it, A or B, and I'm going to build a gate for that, right? AB gate. Then I had another thing, not A or not B. How am I going to do it? Exactly the same way, right? I'm going to have nots for A, not for B, and then go in through OR. How am I going to connect them through AND? It's like building a Lego puzzle, right? You connect them through AND now, right? How I can add OR C to that? Well, I take an output from this big thing we built so far, and I'm going to connect them through the OR gate, and there's an output on it. And this is step by step, first step, second step, third step, fourth step. That's how we build the unit, right? So this is pretty much how we're going to design things. You're going to go from the bottom using the logical expressions, and we're going to build gates out. Any questions so far, guys? Is it clear? I see some question. Let me go one by one. Would it be right to make optimizations? Excellent questions. We're first going to learn how to build it. Then we're going to learn in this class, in the second half of the class, how to optimize it. So you don't optimize first. You first make sure it functions, right? Then you start to optimize it. And luckily in here, we had a good theory that allows us to build optimal circuits, right? So you're going to build it first, and then you're going to optimize it. Bottom means from left always. Yes, we have the mathematical rights when we treat equivalence. So here, when we look at this expression, we handle it left to right. We go to when we parse the tree, we go to the bottom of the tree, and the first thing here is this thing. And then this is the next thing. And then we parse inside of this thing, and then we handle this thing. So it's left to right. You're correct. But remember, this is when you had a logical expression written for you. There are going to be cases where things are not given for you, right? You have to figure it out. So you're going to first build the truth table out of somewhere, and then you can figure out the expression. So how we can create complex circuits? What we do in the case of more complex circuits with several inputs and more than one output. Well, if you're lucky, again, you have a truth table that is provided to express this circuit, right? Usually the behavior of the circuit is expressed in words, unfortunately. Someone tells you what they want you to build, and then your first step is actually to build the truth table that represents the exact behavior. So you usually start with the truth table. For example, I'll give you one example. So let's say someone asks you, I want a circuit that has 3 inputs, A, B, and C, and has 2 outputs, X and Y. And so the first requirement is we want to have some logic that would be used to set X high when all 3 inputs are high. So the question for you, what is that logic that I want to use to generate X when all A, B, and C are high? So high means 1, low means 0, right? How I can build something that only when all 3 inputs are higher 1, then the X is also 1. What would be that logic? You can just type your answer if you want. Yeah, A, B, and C, so all the answers given, all correct. Yep, thank you guys. And then another example, what logic is needed to set Y high when the number of high inputs is odd. So that's a little bit more difficult. Yep, so I think we got XOR from Mohammed and Kevin. Yeah, so using XOR logic. So how can we build this thing? Well, so small problems can be solved easily. That's the whole idea. So if we need to do A and B and C, this is the way we design it, right? It's very easy. If we want to build this thing for odd, we just build it using XOR, right? So, and then you connect these things, right? And I'll show you how. You essentially take your original inputs A and you forward it through some wires here to here. If you make a physical circuit, you literally would gonna put wires from this source into 2 different or 3 different destinations, right? And this doesn't cost you any extra gates, it just costs you some wires. And usually when it tape out in a real chip, it's not an issue. Then you see you feed into some B's as an input here, and then you feed some C's in the input here. So all in all, this is your circuit right at the end. So again, building it from simple problems into more complicated problems that you can build something very complicated. And you would be surprised, but everything your processor does, it just builds out of this very simple logical gates and nothing else. Like everything complicated we do with the computer just built of this very small basic blocks. But obviously, if we're going to deal with something really, really complicated, we need a more systematical approach to make sure that we understand how we build it. So how we're going to build and create complex logic. So the general approach consists of 4 basic steps. First step is we create these truth tables based on the desired behavior of the circuit, right? So you always start with a truth table. It's either given to you or you build it from their word description, but the truth table is required. Then you want to come up with a good Boolean expression that has exactly that truth table. Good involves this optimization that someone already asked about that needs to be done to make sure things work. And then you want to convert Boolean expressions into gates with the approach I already described to you. The key to an efficient design is that step 2, where we need to come up with a good Boolean expression. That's we're going to spend time, considerable time in, second hour of today's lecture. So how to make it more optimal. But before that, what is a better way to represent truth tables? That's the first question asked. Do we really want to write the whole blown table? So let's look at the example of the truth table here. And this truth table represents this function. Y, the output, is high, which is 1, only when B and C are both high. So that's the condition, but you had 3 inputs, A, B, and C. So you had to write the full table that consists of 8 rows in this table, right, with different values. So do we really always want to draw the whole table to express that? Is there a better way to describe the truth table? So this is the first question we try to address. Yeah, so you're going, I think Sophia is looking in the right direction here. So let's see how we can do it better. So really, we just need to express what's written, not the rest. So now we're going to use the new terms that I defined for you in a second, called Minterms and Maxterms, that essentially represent you all possibilities. So what really happens here, if you had a variable A, variable B, and variable C, you try to find all possible cases where, say, A true, B true, and C true. That would be M7, right? And when all are false, this is outside of this circle. So inside circle means true for that variable A, B, and C. Outside means not. And this is all 8 possibilities for 3 variables, right? So this is terms that we're going to use right now. So before I go into that, you're going to see in logic and even the things that we do, there are certain things that use interchangeably, certain symbols. So to avoid the confusions and question about it, I'll start with the notation because you're going to see it interchangeably. So when we use AND operations, the mathematical symbols used are different forms of multiplication. So it's either A dot B dot C, or sometimes dots are even omitted for simplicity, or you use multiplications, or you use this symbol, right? So all of this is exactly equivalent. It's just different preference of notation. There's really no difference. For the OR operation, it's denoted by the add symbol. So A plus B plus C, or A, A, B, C this way, right? So all legit forms. For negations or not, depending on which area you are, you can use this note, you can use apostrophe here, or you can use this bar at the top of the value. All of that means not, right? So you don't get confused. Yes, so as I said, so for the first expression for ABC, you can even omit this dot. So in many cases, I'm going to just write ABC or A not BC, something like that. You're going to see so. And for XOR, that's rarely used in expressions. We use this symbol, circle with plus. Questions wise, why XOR is so rarely used in circuits? What's bad about it? Yes, Calvin, you're right. It's expensive. And I actually show you today why it's expensive, right? With the MOSFET gates, it can take up to 8. So anyway, so that's the reason why you rarely see it in practice. Okay, So a little bit of warm-up exercise. So before we define Minterm and Maxterm formally, and I add you all this complex, not that complex, but still somewhat complex mathematical notation, let's practice a little bit. For the following logic expressions, we have where the values A, B, and C that make expression to evaluate to 1. That's the question. So what is the input of A, B, and C needed to make the whole expression evaluate to 1? Remember, this symbol means not. Yeah? Good job, guys. So all zeros. I hope everyone understands that, right? So the key thing this is this expression and only this, nothing else. That's important things. Okay, let's try again. So how about A, B, C? Okay, wow, amazing. Complete agreement. I wish we have elections like that. Okay, so that's true. So it's all ones. Then how about this expression? Yep. Oh, someone is special. I hope they just converted into a binary and the answer is still correct. Okay. Okay. And how about this last one? Okay, great. So I feel like you all got it. So that's a building block for the Minterms we're going to just build on the next slide. First, I will define Minterms informally for you. So essentially, a Minterms is a formal way to convert your truth table into expressions without thinking. So that's something machines like. Despite all this fuss about artificial intelligence and everything, like I work on machine learning area myself, machines are not as intelligent as it may think. They just really like, very stupid operations, but they're very good at this simple, stupid operations. So what are we going to do here, right? So if we had a truth table like that, right? So what we're really looking at is we take all your inputs, and we sort them based on the values, starting from all zeros, then you take the last value and flip it. And then you go like, flip this to 0 and then to 1. And we put everything in this sorted order according to the ABC expression represented by ABC. So this is the way we store elements in the truth table, and obviously Y stores the output. Then for each row, we find the AND expression that evaluates to 1, if and only if A, B, C are of the values in this row. And we AND those expressions M with an index, with the row number. So essentially what I just said is that every row get a mathematical notation so that we just practiced before, right? So exactly, if we had not A, not B, not C, it corresponds to all zeros here, right? So this is how you just practice each of these expression. This is how you're going to generate it from here. Okay. So this is relatively straightforward. So then each of these rows get M with an index, which is represent the row number. And we start with 0. We like in computers starts everything with 0, not like in math, not from 1. So we go from M0 to M7. And this is how we number all these rows, right? So this is essentially what the Minterms are. M0 to M7 are the Minterms. And they call mean because AND minimizes everything, right? Okay, any questions on the informal definitions before we go to a formal definition? So essentially, when you had a truth table, you can look at the Minterms, right? I don't have any questions, so we'll go look at more formal definitions. So essentially, a Minterm is an AND operation, AND, of true or complemented. Complemented means negated, not expressions with every input present in the form. So essentially, from this truth table, you convert it into this table, right? So you replace these all zeros and all this with the minterms, right? The y is still the same. And then your M0 is essentially not A, not B, not C, M1 is not A, not B, not C, and all the way to M7, right? So this is pretty much the formal definition of the minterm. One question you should probably have by now, okay, a lot of definitions, why is it useful? Well, as you might guess, we were going to use that now to represent any truth table, any functions. So you're not going to guess what the math should be behind it. You just look at the truth table and quickly write down the math. So I talked so far about minterm, which is indexed with a small m. But in parallel to that, I want to mention that there is equivalent notation. There's nothing special about AND. You can also represent everything as OR expression with every input present in true complement form. So you can add it in AND form, you can do it in OR form. Soon you're going to realize why I pick AND as the main representer for some, engineering reasons. But mathematically, minterm and maxterms is absolutely equivalent representations. You can use both. So essentially, maxterms are going to look like that. A plus B plus C, right? M1 is going to be A plus B plus not C, and all the way to M7 where everything is negated. So that's OR instead of AND. So feel something fishy? Well, it is the naming, right? So minterm is about when the output is 1. Maxterm is about when the output is zeros. So when you want to represent a function, you either can focus where it has ones in it, or you can focus where it has zeros in it. Both are equivalent because everything you don't represent is exactly the rest, right? So you can actually use both. For example, not A and not B and not C is 1 only when A, B, and C are all zeros. And for M0, A plus B plus C is 0 only when all of these 3 are zeros. So that's the difference in focus. One focuses on ones, another focuses on zeros. Okay, so we just defined minterms and maxterms. So right now is a little bit of a little quiz for you. I'm going to give you some notations, and I'm going to ask you a questions on whether this is a minterm or maxterm based on the definition. And please, again, use the chat here. So we can't really talk with so many people. Okay, A, B, C. Is this a minterm or maxterm or none of them? So I see minterm, maxterm. So I see one person that is correct. Finally, Part said it's none, and someone said both, that's wrong. And Terry said neither. Yeah, so the answer is none. So it's missing an input, right? That's where the trick was, right? The D, so you cannot miss any parameter in minterm or maxterm. They had to have every parameter either in the original form or in the complemented form, okay? Okay, so the answer is no. Every input needs to be there. D is missing. So you see, guys, there is a point not to share the lectures before, right? I can catch you on some basic questions. Okay, A plus B plus D. Is it a minterm, maxterm? None. So someone says max. More people says none now. Someone says max again. So for people who said max, again, the catch here, C is missing, right? So there is no C. So this is neither minterm nor maxterm, right? It has to have every single term. So you had 4 parameters. You need to have an expression that's going to have all 4 of them on one form, okay? Okay, how about the third one? Yeah, so I think I didn't get you this time, right? This is still neither, right? Why? Because even though there are 2 expressions here, you need only AND and only OR, right? You cannot mix the 2. So for the minterm, maxterm, it should be just one type, right? You cannot mix them up. How about this guy? Got some answers here. Good, good. That's max term. It's a valid max term here. And how about this guy? Okay. Yeah, I apologize for everyone who knows that stuff, and it feels like I'm going slow. I need to make sure that everyone's on the same page because I'm gonna go into more complicated stuff out of a sudden. So I need to make sure you understand all the basic. No one makes mistakes. So yes, this is M5, capital M, and this is Minterm M10. Sorry. Okay, we had someone really smart here. Can we convert 3 into a Minterm with demorgans? Yes, I'm gonna cover that. So that's gonna be all covered. Yes, you can do conversions. You're just ahead of us a little bit. Okay. Given n inputs, how many possible Minterms and Maxterms are there? So this is a little bit more complicated questions. So given you have n inputs, how many different terms you are gonna get? Okay, that's good. Everyone got it right. 2 power n. So both Minterms and Maxterm, the maximum possible is the number of rows in the truth table, and that's 2 power n. It's really exponential. Okay, so we got the basics. I hope now everyone understands Minterms and Maxterms. I show simple examples, so you shouldn't be get confused by missing inputs or using a mixture of and or at the same time. So how are we going to go from the truth table to the logic expression? Everything before seems very hand-wavy. Like we just kind of try to write it down as it looks. We really didn't have a formalism to it. So now we want to do a formalism. So let's look at this huge truth table with 16 rows. So there is only a single Minterm that indicates an input that's set to go high here. What is that one? There's only one that's set to 1. Everything else is set to 0. Yeah, this is M2, or another one, someone wrote AB not CD. Yeah, so which is correct. It's just M2 is a short notation. So yeah, there's only one thing here, right? Yeah. So essentially, if we want to represent this truth table using Minterms, we just write M2, which is not A, not B, C, and not D, right? So this is the example here. So you see why it is, right? It's not A, not B, C, and not D, right? Okay. So again, this is how I can take this whole truth table and replace it with just one Minterm. And that's how it's more efficient to represent it. So it kind of tells you how you represent now any truth table, right? Well, what if I have a couple of ones there? Well, the way I do it, I look at the truth table here, right? ABC, right? And then I look at when I have ones, and you see I had one in the output in M2 position, right? And I had another one in M8 position, right? How I can concatenate them? It's very easy. I take 2 Minterms and I merge them through an OR term. So the result is this output gates, high is in both Minterm, M2 and 8, but in nothing else. So this is just by construction. We construct it such that it's true for M2, it's true for M8, but for nothing else. Yes, that's the correct answer. And we want to describe the truth table with the rightmost column of outputs. So essentially, we take your output, right? We wrote down all the M expressions, Minterm expressions, and then we generate the output as a concatenation and OR of all of this. So this is how we generate a truth table using Minterms. So essentially we came up with a logic expression, and if we had to formally write it, we can just write this: not A, not B, C, not D, plus A, not B, not C, not D. right? So right now, we just look at the table and we get the notation without any guessing, right? We just look at it and generate the table. Any questions here? Okay, when writing your Minterms tables, do you need a column for every one? So essentially, this is right now to keep it simple for you, right? So that I show you how I build it. In reality, what you're gonna do, you're gonna look at the output, you're gonna see every one that it generates in the truth table, you're gonna get a term for that and you can concatenate that, right? Yes, you can only use the notation and quickly generate the results. Yeah. I hope this answered the question. So this is just for simplicity, so you understand why it works. In reality, you don't need this intermediate step. You just look at the truth table and then you generate the equation. Any questions here on how we use Minterms? Like when you see a truth table, now everyone should be able to generate the equation using Minterms for it. If you're not sure how to do it, please ask questions right now. Okay, we got one. It's called Minterm because everything that AND is taking, it's like min functions. You take A and B and you C, and it's only true when you get a minimal of this work. So AND is for min and OR is for max. That's why they got those names. So in this table, M2 and 8 are important because they're the only one where the function gets output of 1. Everything else is an output of 0. So this is why we highlighted them, right? So really what the truth table looked before in the previous slide, there was another column that has 2 1s in it. One is an M2 position, one is an M8 position. So if you had more ones, you will have more important items. This is just an intermediate step you can do in your head. You don't need to write it down. Okay, so let's move on if there are no questions. So essentially we get 2 canonical forms of Boolean expressions. The first one is called Sum-of-Minterms, or SOMs, which essentially takes each minterms and add a plus in between them, right? So this is a canonical notation. For example, you can get something like that: AB plus not AB plus A not B, right? And each minterm corresponds to a single high output in the truth table. And this is sometimes is also known as sum of products, right? Sum of minterms or sum of products, that's how people called it. So when I'm going to use abbreviation SOM, this is sum of minterms, right? So that you know. So this is exactly what we expressed so far. So yes, if there is an nth entry is 1, then we add an n. Yujank, you're correct. Okay, obviously there is an absolutely symmetrical thing you can do with zeros, right? Instead of focusing on 1, you can focus on zeros. So Product-of-Maxterms, that's what it is. So here, each term, instead of ands, consists of ORs, pluses, A plus B, not A plus B, A plus not B, and then you AND them. So instead of doing a sum here for each term, you do a product. So you either had sum of minterms, SOM, or product of max terms, or POM, or POM. So each max terms corresponds to a single low output in the truth table. So here we're focusing on ones, right, on high output. Here we're focusing on low outputs. It's known as products of sums as well. What I want to say is both notations can be converted from one to another using some of the Boolean rules that someone already mentioned here, De Morgan's law, and we're going to talk about it in a few slides. But essentially, each function can be represented in both forms, right? You pick whatever is convenient, depend on different other conditions, but mathematically both approaches are equivalent. Any questions? Okay, so here's one more example. So we are trying to get an equation for y, and we want to write what the equation would be for it. So anyone wants to try to type it in? So this is the original truth table, this is your output, and this is a convenient way I wrote the terms for you already. So anyone want to give it a try? What would be the equations for y here for this truth table? Okay. Everyone was too slow, so I was not patient enough. So it's M2 plus M6 plus M7 plus M10. And this is sum of minterms, right? Okay. Let's try here. So here you see capital M's. So those are max terms. Anyone can write me the equations for y here? I'll try to be more patient this time. M3, M5, M7, M8, M14. Yep. Good. Good, guys. Yeah, that's exactly that. Product of max terms, right? Yeah, I think everyone who responded correctly. Okay, so I hope you got it so far, right? So you see how I can take a truth table and convert it into a mathematical notations with either SOM or POM, whatever is convenient. And you don't need to guess, right? You have the algorithm, an easy algorithm to implement it, and it can be done for any Boolean functions. In writing our answers, do we simply write MI and capital M for the final solution? Do we need to expand them? I guess it depends on the situation. Sometimes there would be cases where you build the real circuits, right? Then eventually you need to replace M's with their A, B, C, and D, right? But in making all the intermediate steps, you can just use M notation. It's all fine. It's just for the final output, for the final results, you still want to use the real, because in reality, when you're going to build the circuits, there's no shortcuts. There is no such thing as M3 or capital M4. This is all our convenient notations to save time and space. Good question. Do we need to then not the whole poem? So it really depends on what you represent. So essentially you can say, give me the function zeros or give me the function ones. And depending on how you write it, you either had an extra not or not, right? So sounds funny, but essentially you had a logical expression that you ask for, right? So that logical expression, usually if you want to give it ones as an output for the circuits, then you do it. But it really isn't, because you really don't need to add not most of the time, because the circuits you build, right? This gives you zeros when they're supposed to go zeros, right? Let's focus on zeros. And everything else, it gives you an 1. So if you make an equivalent SOM circuit that would be longer, that's going to give you exactly ones when it's right and zeros when it's not, right? So just to understand, you like here, we're focusing on y's that are zeros, but for every single other input, it's going to give you the opposite value. So it gives you can build an equivalent circuits using minterms, and it would have more terms, but it would be still valid. Because if you're going to do this thing, this one has 5 terms. If I'm going to do a minterm for it, sum of minterms, I'm going to have 16 minus 5, 11 terms. That's going to be a very long expression here, but they are both absolutely equivalent. There is no need to put a not in front of it, right? It's just one is focused on ones, one is focused on zeros, but outputs are equivalent. Yes, you're thinking right. Yep. So it's like you can look at there, how many zeros or ones your table has. If it's a random function, the number of zeros and ones are roughly equal, but it had a very biased function that had more zeros and more ones, one expression is better than the other one. But remember, each of them can be converted from one form into another form, right? So it's we had a way to, make them look the same if we need. But yes, it's better to start with something simpler. Okay, any more questions here? Okay, so sum of minterms versus products of max terms. So some of the questions you already asked. So sum of minterms expresses which input caused the output to go high to 1. Pom expresses which inputs cause the output to go low. Sums are useful in cases where there are very few inputs combination that produce high output, and POMs is obviously useful when expressed in truth tables that have very few low output cases. So if you had a bias in your output, too many zeros or too many ones, one is better than another one, okay? But otherwise, for a random function, there's really not much difference. So essentially one question I'm asking you, what would happen if instead of you using this truth table with 4 expressions, what would happen if we do it with product of max terms? What's going to happen? Don't give me the equation, just say why would be problematic. Yeah, it will be quite long. Like if it's automatic, it's not a big deal, but still, instead of having 4 terms, I would have to write 12 terms here, right? I think everyone understands that, right? Yeah, it will be 12 terms, yeah. Yep, exactly. So this is the reasons, and same problem here. If we do this using SOM instead of product of max terms, we would have too many ones, so we're gonna have 11 terms here. Okay, so this is, I think, a natural a natural place to make a short stop. So I will have a break right now. I say until 12:10, right? And let's continue. If anyone has any questions at this point, please post them right now. Otherwise, I'll see you back in 10 minutes. And thanks to everyone who used their cameras. I really appreciate that. It was very helpful to see your reactions. So if you can occasionally keep doing that, that's very helpful. Thank you. And see you in 10 minutes, roughly. Okay, there was a question here. Can you explain the difference between min and max term once more? Okay, so I'll try it once more again. So essentially there is only one truth table. This truth table, let me go a little bit back. So forget about this part here. There's A, B, C, D, and there is an output. Output has zeros and ones. So one focuses on ones only, right? That's a min term. And it expresses the function as this is 1, this is 1, this is 1, this is 1. And you get mathematical equations to get that. The other one focuses on 0. So it writes a function saying this is 0, this is 0, this is 0, this is 0, and everything else is 1. So they are equivalent, it's just a different form to represent the same information. And one is sometimes better than other because there can be disparity between the number of zeros and ones. Did I answer your question? Anshu? Okay. Yeah, we will keep playing with those. So the really equivalent is just a different representation. They're mathematically equivalent notations. You can convert one to another. It just one is a simpler equation than other in some cases. Okay, see you guys in 10 minutes. There are no more questions. Okay, we're about to start in 1 minute. Okay, let's continue. And for people that's still comfortable turning on their videos, please do so. Okay, let's continue. So we learn about Sum-of-Minterms, Products-of-Maxterms. Obviously, this is an important step, but we eventually need to convert it into logical gates. So how are we going to do it? Well, actually, if you think about it, it's relatively straightforward, right? One, now when we had all these inputs, right, we just feed them into the corresponding units, logical units, and we can then generate a cool output. So for example, here we have M0, M1, M2, and M3, and overall, that's the logical expressions we're dealing with, right? Not A, not B, and not C, and so on. So this is exactly what the Y represents here. And this is how we generate it. So I guess you guys like to replicate me, so that's funny. Okay, let's move on. So does it feel like we just solve everything? We just generate on this previous figure there, you know, the circuit. Was it a success, or there's something still left to do? What's your opinions? Okay. Any questions, any opinions? What we're gonna do moving forward? Yeah, this question happened before, and the answer, you don't, because think about it. One function generates an output, and you focus on figuring out its zeros. This is for POM, right? But everything else is automatically ones. So it automatically generates proper outputs for all the ones, right? Because it focuses on zeros. Another focuses on ones. So it automatically generates all the proper zeros as well, whatever doesn't fit it. So you don't need to add any extra not at the end. No, that is actually not correct. So you get POM and SOM, and all of this are two representations of the same function. You don't need to negate anything. It just, when you build one, you focus on the functions ones, and everything that is not one automatically zeros. And the second one is the other way around. So you get one formula for one and another for another one. Yeah. Now, it's a reasonable question. Now, you don't need to negate anything. The fact that you focus on one versus another doesn't really change the story. Okay. Any more questions? Okay, let's move on. So the answer to this question that I still didn't hear, because I guess a lot of students were focusing, you know, on putting a background with my image. The main issue here is really it's not done yet because it was not optimized, right? So that's the main problem. Like when we want to build a circuit, we want to make it efficient, right? It's not about just building it, it's about making it efficient. And this is something we really want to potentially do in the next slide. So why we want to reduce the circuits? Just look at the examples on the left and the examples on the right. This is actually, if you look carefully, two equivalent functions. So you can see if I'm going to use it the way I do from the truth table, I just wrote a lot of redundant gates, right? I really wasted a lot of gates. So the next question is, after we were able to build a truth table, and then we're able to convert it into the correct output, and we're able to get a math formula for it, how we can make it efficient, right? So to minimize the number of gates, we want to reduce the Boolean expression as much as possible from a collection of minterms to something smaller. So minterms are cool because they're easy to generate, but we don't want to stop there. We want to simplify them. They had a lot of redundancy. This is where the math skills come very handy. Okay, let's have a look. So I will remind you a few basic identities that you probably learned in other classes. They're relatively straightforward. So commutative law, so x and y equals to y and x plus y equals y plus x, associative laws. A good question, actually. So is a circuit better if it has less logic gates? So the question is not all gates are equal. So from mathematical perspective, it's just better when it has less. The types of gates also matters. We're going to cover that eventually. But for now, you're focusing on having as fewer gates as possible, right? That's your goal. But we will talk about what the minimal really means. Right now, we're focusing on minimizing. I don't think I skipped anything. So it was just maybe covered hidden slide. So associative law, x and y and z. So you can just move the brackets and say associative law for or plus. And there is a distributive law as well. So how to open the brackets, right? So it's similar to the algebra and calculus you learned before. It's the same thing here for Boolean expressions. Any questions here? Is this all clear? Okay, then I'll go a little bit faster. So other Boolean identities, that's something that was mentioned before, and that's super important that I want to everyone understand. It's called De Morgan's law, right? So how does that work? So the way I like to think it's about how you propagate the not inside of the expression. So I usually read these laws right to left rather than left to right. So we had x plus y, and when you put not in, the nodes goes to the individual terms, but plus changes to dot, right? Or changes to and vice versa. So if you propagate not, you get it to each individual term, but on the way the math signals and an or flips, right? That's De Morgan's law. That allows us to potentially easy to flip things if we want. So how the best way to think it in the graphical form? I had these two nodes here, right? I feed them into this AND unit, and as I feed them in, it flips from this type into that type, and the NOT comes out on the other end. That's the best way to think about it, right? Okay, and the same with OR. You put two inputs in, and it flips, and you get the NOT on the other end. Okay. Okay, let's move on. So De Morgan and Nandi gates. Okay, so as you can see here, De Morgan's law is very important because it allows us to flip the gates to the one we like. And it happens to be that the most cheapest ones to fabricate is NAND gates. Those are the cheapest one in manufacturing. So essentially, a sum of products circuit could be converted into equivalent circuits of NAND gates. So if you have something like that, it really can be converted. So if you had an OR of 2 AND gates, it can be converted into 3 NAND gates. How so? How did I get from here to here? Well, I just applied the De Morgan's law. I started from here, and then I added not here and not here, not here and not here, which is absolutely equivalent. If I had an output here, right, then that not is doing through 2 nots, so it's exactly the same as before. Then I focus on these 2 nots going through this OR, and based on the De Morgan's law, when I get these 2 nots, it flips to AND with not here. And if you look carefully, these 3 guys are really just 3 NAND gates. So essentially, the reason why we like Minterms so much is everything that's written as OR of ANDs is immediately converted to just NAND gates, right? So those are the simplest possible gates, and this is the one that we can get it. So essentially, that explains us if we can minimize the Minterm, right? Then it really will minimize even the physical layout, because you can easily generate the equivalent number of NAND gates for that, right? So if you had this form, it can be always converted into this form, right? That's straightforward, just based on De Morgan's law. And the number of units is identical. And this not, you don't need to count, mostly because it's going to be converted into one single unit. Any questions here? That's very important. Any questions about De Morgan's law? I understand that everyone has a different background in math, so it can be easier for some people, harder for others. Okay. Sure. So, few questions. So we have to use NAND whenever we can. So the thing is, you don't need to think about it too much. Remember the power of abstraction. Just generate the right, logic gate using sum of products, right? And that would be very trivial to convert it into NAND gates. But moving forward, if you're going to build something of your own, something different than Mixterm, that's a good thing to think about, using NANDs more than others, right? But in this case, it's trivial. You just convert it automatically. So another question from Terry, can you explain again how the OR turns into NAND gate? Okay. Okay, so that's based on the De Morgan's law. So let's look here. So this is your AND gate. This is another AND gate. This goes into OR gate. So what I do this virtual trick. This is the output on the end. I add one NOT and another NOT here on the same channel. 2 times NOT is cancel out. So essentially what I did here is equivalent to what I did here. Is this part clear? So I just manually added 2 NOTs, right? So then I look at just this piece of the circuits. I have 2 nodes here and 1 AND here. This is based on the De Morgan's law. If you had not X or not Y, that means AND and negations of the output of all of it. This is just based on the De Morgan's law. So this guys here is a NOT of an AND, and this is exactly the same as NAND gate. Okay, cool. Let's continue. Okay, so now we're going to talking about more interesting stuff, which is reducing Boolean expression. So assuming logic specs at left, we get the following here. If we had this truth table, we get M3, M4, M6, and M7. So if we had a truth table with 3 variables of this kind, this is the expression we're going to get. We just practiced before, and this is the equation. So how are we going to optimize this? There is some complications I'll show you. So before we go into that, a little bit of warming up. So if I had an expression like that, a and b plus a multiplied by not b, how you can simplify this quickly? Yes, exactly. So everyone is correct. You pull out the a out. You pull out the a out. In the brackets, you get b plus not b. B plus not b means just 1, right? And the a and 1 is just a, right? This simple, so you just apply, two identities, 3 identities actually, and you just get that. This is a very handy thing that we're going to use right now. So just remember about that. So reduce by combining two terms that differ by a single literal. So if everything is equal and just only single literal flips, you can get rid of that literal. Okay, let's look at this thing here that has 4 different terms. How we can simplify it? Well, I see this obviously, right? If you look at this, there is AB here, right? AB here, and we're different by C and not C. So by using the same tricks for the whole A and B, we can get a simplification. We just combine the last 2 terms. We get AB here and these 2 terms here. And when I look after that in this expression, I don't see an obvious optimization anymore, right? It seems like I cannot apply this trick anymore. So it seems like we did our best, but did we really do the best? Did anyone see we can do something better than what I just did? Yeah, so several people noticed that. So I pick these 2 somewhat at random. Instead of picking these 2, I could have picked this pair and this pair. Let's see what happens if I do it in a different order. So if I do these guys, they're different by B and not B term. So I can apply these things to them and just get A, not C. And the same trick I can do here. They're only different but by A term, right here. So if I do this and this, I will get that. Sounds like a nightmare. It seems like depending on the order in which I apply, I might get a worse circuit or better circuit. So again, we need a system, right? It seems like if we're just going to apply those identities without any particular idea behind it, I'm going to be in trouble, right? I'm going to be in trouble because it's not clear whether I got anything optimal. So we need a mechanism to come up with an optimal thing, okay? So there should be a way of combining that we would find terms that are simpler than others and we know that they're optimal. So this is our goals right now. How to get the simplest expression. I'm going to define what the simplest really means in a few slides. So it should be still something that puzzles you what the simplest really means. But eventually the goal is to find something that would look like more or less optimal. So what is the simplest? You, as an engineer, working in, say, a company like Intel or NVIDIA, you can get your boss to tell you what the metrics that really exist. So simple might denote the lowest number of gates. So you just count the number of gates without counting not, and the lowest number of gates when you count the nots. So this is 2 metric. We can call one of them gate cost or G, and another one GN that includes the nots. So let's look at this circuit, and please tell me what would be the G of Y for this circuit. So again, type as usual in the chat. Yeah, so GY is 5, like everyone who gave that answer is correct. How about GNY? This is a little bit trickier, so think about it, don't rush with the answer. So several people said 9, but does it have to be 9? Oh, someone said 7. That's impressive. Okay. So let me show you the correct answers. So 1 is 5. That everyone was correct. The other one is 8. Why is it 8? Well, the reason is because I would need to do not B. There is no shortcut here. I would need to I need to do a not A. But not C, I don't really need to do it twice, right? I would have an input C. I would put a NOT gate in front of it, and then I could have two wires, one going here and one going there. So I'm not going to be, if I'm not dumb, I'm not going to use two NOTs here, right? So essentially the answer is 5 and 8. So this is, you see how things can be complicated. Yeah, so you don't want two NOT for C, it's a waste, right? There's an obvious way to do it better than that, right? So depending on which metric you use, you can either have 5 or you can have 8, right? But this is kind of give you a feeling of what the simplest really means. Usually we focus on just the number of these big gates without NOT, but the NOT gate is still a gate, even though it's very cheap. So the trick here, don't count NOT C twice. Okay, now we're going to cover something called cardinal maps, which is the finding the simplest expression systematically, right? So these maps, or sometimes called just K maps, you're going to use a lot, and that would allow us to find the minimal thing, again, without too much thinking, something the computer could do. Okay, so the goal is to reduce the Boolean expression. So how do we find the simplest expression for a circuit? The technique we're going to use, called K-maps or cardinal maps, are a 2D grid of minterms where adjacent minterm locations in the grid differ by a single literal. Oh, like, oh my God, that looks very complicated. It is not. Like, look here. So for example, not B, and you're just different by a single literal, right? You place things in the table such that there is C, not C here. Here you put another table, A, not A. Here again, you're only different by one literal, B and not B. Here again, you're different by just one literal, from C to not C, always just by one literal, and the same thing here. So this 2D map of minterms, why it's minterms? Because really what happens here, it's this multiplied by this, right? So not A, not B, not C, this is this element from the original truth table. We just take the truth table, and from a linear sequence of rows, we convert it into this form. Okay, does it make sense to everyone? Okay. Any questions here? So this is where it really is. Okay, so let's look at this. So this is your original truth table. This is the cardinal maps, right? This is how it looks like. They represent absolutely the same information. If you're going to just look at the ones in this table, they're still there. There is one is A, not B, not C. A, not B, not C. You see here, right? So each term in this table maps to something in this table. So we really didn't change anything yet. The cardinal maps is really just a different representation of the information you store in the truth table or using minterms, right? We didn't really change, we just store it differently. But the way we store it is actually helpful, right? This is something that would allows us to do some extra optimizations. Okay, so let's look at another example of cardinal maps. Let's say if I had 4 variables, I had some flexibility how I can write things. They can be of any size and have any number of inputs. So essentially, what you can do 2D by 2D, right? So there are 2 dimensions here on C and D and 2 dimensions here on A and B. And those are the minterms. There are 16 of those. And this is how they're going to map here. You see, since adjacent minterms only differ by a single literal, they can be combined into a single term that omits that value, right? So this is the key idea. So essentially, the idea is if I had a sequence of things, right, that happens to be the same value 1, I can now replace it with a single literal. So how does that work? It still sounds too complicated. Look here. So for example, if you look at this column here, right, you see we have BC here. And then we had one for not A, BC, and for A, BC. Both had one. Well, if you can group this thing together, it really means A or not A doesn't really matter. It's ones, no matter whether it's A or not A. So when I'm gonna simplify my Minterms, instead of having not ABC and ABC, I just have BC alone. So that grouping by using rectangles would help me to do optimizations without thinking too much about it. I just look at the table. So essentially, once kernel maps are created, you start to draw boxes around groups of ones, high output values. And boxes has to fill in with certain rules that I just described to you. There are 4 rules here. They need to be rectangular, right? And needs to align with the map. So something like that is fine. That's rectangular, it's 1 by 2, and it's aligned with the map. Number of values contained within each box must be power of 2. So I cannot have 3 or 5. I can have 2, I can have 4, I can have 8, right? Boxes may overlap with each other. We will see the examples soon. And boxes may wrap across the edge. Why the wrapping across the edge is fine? Because if you look here, they're still different by 1 literal. B, not B, and not C for both. So you can actually group them. They just happen to be on the different sides, but there's no different from if they were here. So this is a 4 major rules for K-maps. If there are 3 ones together in the same row, I had to group them separately. I had to group 2 together and 1 together, because 2 power 0 is still 1. So individual elements still power of 2, but I cannot have 3 together. I can have 2 separately and 1 separately. It means there is no extra simplifications. I'll show you right now with a lot of examples how it works, and but those are just the rules. Remember, has to be rectangular, has to be aligned with the map, number of values has to be power of 2, boxes can overlap with each other. And our goal is essentially to cover the whole ones with as few as possible of those boxes. This is the game we're playing. This is what optimization comes to, which humans are very good at. They actually like thinking about not algebraic expressions. They actually like thinking about covering things with boxes. Okay. We got a few questions. What happens when there are 3? So this one is the second rectangle of the expression, not CA. Okay, I don't really understand the second part, Terry, of your question. So essentially, if you had 3 ones together in the same row, you just have to group 2 together and 1 separately. Yeah. Okay. Let's look at more examples. I think it will get clear if you get more examples, and we're going to practice. So what you're going to need, I'm going to show you something I'm trying to do with a truth table. You need to say me that is acceptable or not acceptable, and why. Ivan asked good questions on how can you group things in this case. It's really the algorithm doesn't define. You can pick any one. You can pick the first 2 and then another one, or the other way around. You have flexibility. It doesn't going to change the complexity of the formula. So yeah, Terry said cannot group like that, not a rectangle, and that's a correct answer. Everyone sees this, right? That's not a rectangular shape. So this is not okay to do it. Yeah, 3 elements, yeah. Yep. Okay. So how do you handle that? You handle it with 2 2s, right? That they can overlap, and that's an acceptable thing, right? So 2 boxes overlapping each other is fine. So overlapping is fine. So you're going to get 1 equation related to that and 1 equation related to that. So you're really going to get like not A plus BC. Okay. How about this guy? I see, right? Yeah, 3 elements. So that cannot be optimized this way. Number of value contained must be power of 2. So how, if you get one like that, what are you going to do? So it's actually okay to have it, right? Because 2 power 0, right? One element, you can always have it. You don't really optimize anything by doing that. You can always wrap up things. It's not very optimal, but sometimes that's the only option left. Yeah. Yep, this is just one term. Is this illegal? So someone says no. So why not? This is actually totally legal. It's 2 by 2. So if you're not sure, please ask an extra questions. But I think everyone got this is 2 by 2 totally legal, right? Yes. So essentially, well, it's essentially just C because A not A is irrelevant, B not B is irrelevant. So this is just C. Everyone sees this, right? Like how we just take something that looks a little bit complicated, not too complicated, but we just simplification took just a second, right? We just get one term. The columns doesn't have to lie in any particular order. It's up to you. And to be honest, that might affect the optimizations, but usually you just go with the original order of variables. Remember, in this case, it doesn't really matter because if you can wrap around this edge, it doesn't really matter. So if I would do them in a different order, I would have 2 by 2, one direction in this direction, right? I can still have it. So it usually doesn't really mean much. Okay, so rectangle with power of 2 entries, all fine. How about this guy? It's 2 by 1. Yeah, that's illegal. No diagonals. Yep. Must be aligned with the map. We cannot cross. How about this guy? Okay. Sorry that it takes that long, but I need to show you every single corner case. I'm pretty sure if I don't show at least one corner case, someone is going to mess it up. So, and you're going to play with this in Logisim, right? So you need to make sure you understand K-maps, how to simplify the circuits. So that's why it takes a little bit longer. Yeah, someone is asking, what is the expression for this one? So does anyone want to take a turn? Like, what would be the expression for this guy? Yep, that's great. A and not C. Yeah. So essentially, if you look at that, it's very easy to guess. So you see A matters here. It's A for both. But B and not B doesn't matter, right? So it's really A and not C, right? So this is the way you see it. You got it, right? That's how you get it. And you see this representation, even though I give you a lot of definitions and all of that, at the end, it turns out to be simpler. I don't need to think in which order to do what, right? I just look at how I cover ones with rectangles. That's a much easier problem for humans to do, even for computer, than the original thing where I need to try any possible combination of algebraic equations, right? That was much harder to play with. So wrapping across edge is fine. Okay, so the question is, how do we find the smallest expression? So minterms in one box can be combined in one term, right? And essentially, instead of having these two expressions, we just have BC, right? That's it. So you had one full column, that's what it is, right? So it's relatively straightforward after you have the K-maps to generate the results. Optimizations are all done. The complicated part really boils down to how you cover with those rectangles, right? After that's done, everything else is trivial, right? So you just write it down. So essentially, the simplest expression corresponds to the smallest number of boxes that cover all the high value ones. That's what it is. So essentially, if you look here, there are two possible strategies to cover. You could have done this, right? Or you could have done this. And this is better than this, right? Because one has two boxes and this has three boxes. So this is going to have three terms and this is going to have two terms after optimization. This is why one is better than the other one. And this is how K-maps help you to see that right away, what's going to be simpler than another thing. So each box should be as large as possible. That's one strategy used. Usually use called greedy algorithm. You try to get as big a box as possible. That's always an optimal strategy. In this case, it does work. So if you have something like that, you should do that or do that, right? So the idea is you should do this thing, right, with the overlapping. Why? Because the more you have here, it means the fewer terms you're going to ask. So first you try to optimize for the minimal number of boxes. Then you're trying to make each box as large as possible. So if you had a choice between this and this, you're going to pick that one. Does everyone understand why this is better than this one? Or it's not clear? Yeah. So if you had just one term, you would have to do not and not B and C. And this one would be the same for everyone, right? It would be just B. But if you do this, then you get rid of one term, right? You get rid of B. So you save on one and, right? So this is always better than this one. So first optimize for the number of rectangles, then optimize for as big rectangles as possible. Okay, so now remember that original examples were all started where I try to convince you that it's a difficult problem, where I first combine these two, right? So really what I did when combining these two was using this type of shape in K-maps, right? I was combining these two and these two separately, and that's why this formula has three big terms, right? But if I would actually have K-maps, I would look and do it this way, and then I would get this equation instead. So K-maps add a system to what we do. So whenever I have a circuit, we had a good strategy explained in a few simple steps that allow not to make these suboptimal decisions. Instead of having longer circuits, we get more optimal circuits. So you just need to follow these rules, and that would help. Okay. Any questions, guys? I hope I didn't lose you. So I thought I was really methodically slow explaining it, but remember, it's the first time I'm explaining you to a second-year student, so I just want to make sure you guys got it. So please, any questions you have, ask. It's totally okay. Thanks, Sam. But people that are, there are always like with 100 students in a class, there's something is clear for others, might not be clear for some other people. So is it any other questions left? Is it clear how it works? I'm going to wait for a few more seconds until to hear any questions. I think I covered every corner case possible here. Okay, so if there are no questions, so essentially those are the steps you have to do. Given a complicated expression, convert it to Sum-of-Minterms, right? That's your first step, right? So you get your truth table, right? From truth table to get Sum-of-Minterms. That's what we did in the first hour, right? How we collect it. Then you draw a 2D grid, right? And then mark all the high values once, according to which minterms are in the Sum-of-Minterms. And draw boxes that cover once. And first, try to find the smallest set of boxes that covers all once. So your first strategy, have as few boxes as possible, because that's the biggest optimization, right? You reduce the number of big terms in your pluses. And then to optimize the individual terms, you try to route a simplification such you try to have the as big boxes as possible. After that, you write out the simplified result according to the boxes found, and that's a straightforward now because you see all the redundant variables there. Everything that, when you flip over in the rectangular box, that's something that goes away. If you had B not B across the edge, that's something that goes away. Only whatever is relevant stays. Okay, just to finish all this up, everything I just said, that is not restricted to minterms. It can be also done with max terms. So similarly, although we're not going to do it, you can do the same thing with max terms, right? You can use capital M's, right? And you can look for all the additions, and then you do AND for those additions. Corner maps with max terms works absolutely similar, except that now you focus on 0 entries and group them together instead of grouping the entries with 1 values. So you focus on zeros instead of ones. Can someone guess why do I focus on minterms more than max terms? Mostly, like I show it's symmetrical from mathematical perspective. I mentioned it several times, but I'm just curious where you guys got it. Why do I prefer to talk mostly about minterms? Not really, Terry. It really depends, right? So it doesn't have like I do focus, and not necessarily more intuitive. It's like it depends on here. Yes, cheaper. It's all about cost in this life, right? So it's not because it's more intuitive, not about fewer ones. It's cheaper. Remember, I showed with the De Morgan's law how to convert it very easily into NAND gates, and those are the cheapest, right? So that's a very straightforward conversion. That's very easy, and that's why people prefer to talk about minterms. Although mathematically, all of that is equivalent. Okay, so let's now 2 hours of our work together today together. Let's formulate the whole flow that you need to follow if you want to go from from the circuits into gates creation. How are you going to create your own circuit? First, you understand its behavior, and you build and write the truth table based on this behavior. Then you write SOM or POM of that truth table, right? Sum of minterms. Then you take the sum of minterms, for example, and use K-maps algorithm to minimize and optimize the size of the circuit. So after you apply it, the equation you get is not more in SOM form, because now you're going to remove some redundant terms, right? But it's not a problem, right? We use SOMs only as an intermediate step to go from a truth table to the right equation that gives us correctness. K-maps gives us optimality. So at the end, we get the circuits that is as good as it can be in this case. Then after getting K-maps, we take that circuit and translate that simplified logic into the circuit with gates. So essentially we did all the steps together, right? You understand the problem first, build the truth table. That's your first step. Then convert the truth table in SOM form. That gives you the right, answer, but it's not optimized. Then do optimization with K-maps, and then that's directly translated into gates. So if you want to build a circuit of your own, that's the logical steps you need to go to do, so you actually don't waste time and power. Yeah. Is it possible to go to the K-maps strap from the truth table? To be honest, SOM is just a different representation of the same information. So you're going to logically still do an SOM just without calling it, right? It doesn't really matter whether you write it down SOM or not. We want to make sure when you show us your work or intermediate steps, you show us how you do it so you understand it. Obviously, there are tools right now that are going to do it for you. And those tools not going to formally write down the SOM form. They would just go directly to K-maps, right? It's like in calculus, when you had some intermediate step, you can bypass some intermediate step because they're obvious, but you'd really do this. You need to build the truth table first. That's unavoidable. Then you look at ones on this table, and those ones are SOM elements. Then you would need to anyway write, convert the truth table into some form, and that form is really represent the SOMs. The minute you wrote this K-map 2D grid, it really has SOM on it already. You don't need to write SOM separately. It's in this table. Does this answer your question? Okay. Any other questions, guys? This is pretty much the flow. And this is what you need to do when you're going to do your future labs, right? When you optimize things. Start with the truth table, do the work with it, generate SOM, simplify it with K-maps. Can we do a simple example from truth table to simplified expression? Well, that's what we had before. I'm happy to go through it again. So this is a relatively simple example with just 3 variables, right? So I showed, if you want a truth table for it, you can just plot it yourself. But really, it was, how would I put it? So essentially, it has 3 variables there before, and you had, this was the first 3. So if you would plot it, you would have the y output would be this column, and then you add this column to it. So these 2 columns together would be your truth table. So what you do then, you split it by A, not A. So you make, instead of 1 column with 8 values, you had 2 rows, right? 1 by, 2 by 4, table. That's how you go from a truth table into this form, right? And then if you look at just ones and you want to write down, SOM form, that's what you're going to write. Well, the original one is there are 4 of these terms, right? And then essentially how we simplify it is we look at different ways to cover. So this is one way to cover with 3 rectangles, but there is a better one with 2. And this one is indeed better based on the rules we set because it leads to 2 terms. So how do we get from this covering this math? Well, we look here. Across this column, only A changes, BC doesn't change. So it means that A is irrelevant. So you get 1 term that is BC, right, from this thing. You look for here as well. So what changes what not changes is, what changes is B, not B and B. So you get A and not C, and that's the second term. The number of terms here matches how many rectangles you have here. That's it. And this pretty much is about with, with 2 variables, it's too trivial. Like all the circuits for 2 variables, they all convert it into, and or not. Like there's really nothing interesting to do with 2 variables. So this is really as simple as it can be, because with 2 variables, every single circuit has a simple implementation. Does the order of the name rows matter? So here's A not A, and can be A then. Now, you can, you want some order for yourself, not being confused, but it doesn't really matter in the final output, one change. What happens if every value is 1? Well, then you get an amazing function that has 1 huge rectangle, which really means that your function is just straight equal to 1 always. So all variables A, B, C, and D are irrelevant. It's my perfect optimization. Everything goes away. So just 1 term stays. Same with all zeros. Does it answer your question about Eddie, about every value being 1? Yep, tautology, yep. Theory is correct. That's how it's called. Okay, any other questions? Okay, so this is the thing. As I said, everything can be done with Maxterm, and then finally we can do circuit creation. When you say, Farhan, when you say, do we need to use this technique? When you say this technique, which technique you refer to? Yes, you need to be systematic to simplify. So doing it by hand would cause errors. So yes, we would expect you to do K-maps. Should be the final step to replace with an ND where possible. You shouldn't worry about that. I show you why it can be automatically done to an ND. So you just give it that. The rest is trivial. So you don't need to convert it to an ND gates. I didn't, so that's a major part of lab 2, but I didn't check everything, like maybe there is something else. But this is pretty much what you're doing, I believe, for lab 2, but I didn't look at it yet. So I think it's out. You can look at it, but yeah. So I'll check later to answer this question precisely, but I think that's the majority of what you need to do for the lab 2. Maybe the only thing. Okay, any more questions, guys? Well, when you're gonna build the real circuit, right? the K-maps will do this transformation for you, right? You're not going to manually remove B. So essentially in the example you said, you had that optimizations, these conversions that actually good questions, how much it's going to help, because you really still do, you're going to do 2 multiplications and another 2 multiplications. So it's 4 and 1 end. And here you're going to do 1, 2, 3, 4. Yeah, these conversions might be useful in some case, right? But that's not something that K-maps can help you with, right? That can help you to save another gate potentially. Okay. Any other questions? So there are still other tricks that you can do with circuits we don't cover with K-maps, but that removes the main complexity. It removes all the redundant terms. You can make tricks where you replace something that is more heavy with something a little bit lighter. And that's what people do when they really tape out the real circuit, right? For the lab, you need to show the basic stuff. And if you want to do something extra, you do something extra and show that to TA that you can do it even better than just based on K-maps. But this is more like micro optimization versus the magic. Most complexity goes away with K-maps. Okay. Any more questions, guys? Yeah, to get to more. Yeah, so there are a lot of different things you can play with. Sam is right. The question is, what is cheaper versus not? Because XOR is also more expensive than others. So there are like different things you can do. Yeah, I think we're changing to Quercus instead of Marcus, because it seems like there's not a lot of benefit for us to use Marcus. Okay. So this is just a summary of today's lecture. So we learned how to create a logic from scratch, given a desired digital behavior. We had minterms, maxterms, and definitions, and we got the intuitive understanding why they need it. We use K-maps, algorithms, to reduce the size of the circuits. And next week, we're going to talk about building larger logical devices out of these small circuits. So we had this question at the beginning. I'll just repeat the answer. Quiz 1 might have everything that was covered in both lectures, although it's going to be mostly focusing on the first week rather than the second week, but we're allowed to have the material from the second week as well. Okay. Okay. Any other questions? Okay, I think we're then done for today. Thanks everyone, guys. And I really appreciate everyone who turned on their videos today, guys. Thanks a lot, it's really helpful to me. So yeah, thank you. Have a good one.